So let's consider a couple of examples here with cylinders. Let's imagine we have a wire, and the wire is lambda 1, okay, and we have a cylinder around the wire. And let's say the cylinder has radius r and has lambda 2 along the cylinder. In other words, that if you take a certain length of the cylinder, it has a certain amount of charge in it. So we have some length of cylinder, and lambda 2 is going to be Q2 over L. It'll be how much charge is in that length. And what I want to know, if I'm some distance r from the center of all this, then what is the electric field there? Okay, so in principle, that's really nasty and complicated because we have a whole bunch of DQs all along here that we have to add up. We have DQs all along here that we have to add up. And so this becomes a very nasty, very icky, very disgusting, and very, very awkward set of integrals to do. So we don't want to do that. Okay. So how do we avoid doing all those terrible integrals? Because again, we want to do integration by avoidance. Okay. All right. So what we do is we take note of the fact that if these things are all very long, we do know that the DQs here and the DQs there are going to balance out, and so the electric field is just going to point away. Okay, so with that, I can imagine a great big cylinder out here. Okay, and so that great big cylinder out there is going to have integral E dot dA is enclosed charge over epsilon naught. Okay, and so the integral E dot dA is just going to be equal to, well, that's E dot dA of the ends. Well, the electric field goes straight out, just as with the previous example, that's 0. Okay, and then E dot dA here is just going to be E times A, because the E is going to be constant because I'm the constant distance r away from the center here, so everything's symmetric. So E is constant. It comes out of the integral just like before, and so it's just going to be equal to E times A. So E times A is going to be equal to enclosed charge over epsilon naught. Well, that means the E times A, well, that's going to be 2 pi r times L. The enclosed charge is going to be the total charge enclosed. So that's going to be lambda 1L plus lambda 2L. Because if you think about it, here we have this, okay, we got lambda 1 on the inner part, we got lambda 2 spread out on the outer part. So if my cylinder here is some length L, then the charge in this part is going to be lambda 1L. And the part here, due to that cylinder right there, is going to be that charge there, Q2, is going to be equal to lambda 2L. Okay, so the total charge is going to be the sum of the two. Okay, and we look at it and we say we can factor out the L's. And so what we have is the electric field is going to be lambda 1 plus lambda 2 divided by 2 pi r, or 2 pi epsilon naught r. Done. Okay, avoiding all the nasty integrals. And so now if we know lambda 1 and we know lambda 2, then that means we've got the electric field for this rather complicated sort of scenario right there. Okay, well, that raises yet another question. What if lambda 2 is negative lambda 1? So in other words, this is like a coax cable where the inside's positive, the outside's negative. What would that do to the electric field outside if the charges are equal and opposite? Well, look at what the electric field would be. 0. That means all the electric field would just do that. It would start on the inner one, end on the outer one, and you're done. If you're outside, there's no electric field. If you're inside, there is an electric field. So now the question is, what's the electric field on the inside? So if you're some little r, so let's say now r is less than big R, so what's the electric field on the inside? Well, okay, it's going to be just lambda 1 over 2 pi r epsilon. Because remember, EA, so I can do the same thing. I can do like before. I know the electric field just going to go going straight like that. Okay, so I can make a little cylinder right there, a Gaussian cylinder. This is my little imaginary cylinder. I know that integral E dot dA is enclosed charge over epsilon. I know that E dot dA is 0 on the ends. It's going to be E times A around the side of this thing. E times A is just going to be equal to E times 2 pi RL, and the enclosed charge is going to just be lambda 1L over epsilon naught. Okay, and so the L's cancel, and I get that. Okay, so that means it doesn't even care what is on the outside. The only thing that matters for the Gauss's law is what's on the inside of that imaginary little shape that we made. Okay, so our Gaussian surface, this little Gaussian cylinder in there, that's the only thing that matters. It's what's on the inside. It doesn't really matter where the electric field's going. It just matters where it's coming from. Okay, so that's how we would solve that problem right there. Okay. And by the way, even if lambda 1's not equal to lambda 2, this is still what you get if R is less than R, where we're assuming that R is the radius of the cylinder. That's still the same. Okay. Doesn't change, because what's happening in the cylinder is outside. And only the enclosed charge matters.